Moving to chapter 14, which is going to cover the gas mixtures. Here's the objectives, but we're basically just looking at the gas mixtures, predicting PVT behavior, things like that. Okay, so to determine the properties of a mixture, we need to know the composition of the mixture as well as the properties of the individual components. So what that is saying is it's saying, hey, we not only need to know the properties of the mixture, right? And we know what our properties are. What is the saturated temperature of the mixture, things like that. So we not only need to know all of those properties, energy as a property was thrust forward with the first law of thermodynamics. So we need to know all of these properties of the mixture. We need to know the composition of the mixture, right? What is composed of? Is it a pure substance, a single substance, or is it multiple? Like water is H2O, so it has H and oxygen, hydrogen and oxygen. So we need to know not only that, but we need to know the properties of the individual components, okay? And so we need to know what those components of the mixture and of the the hydrogen and the oxygen within it. We need to know everything on a molar level, right? So therefore, it's a molar analysis, specifying the number of moles for each component, okay? Gravimetric analysis, specifying the mass of each component. And here we have the mass fraction and the mole fraction, okay? And then here it uses H2O. The mass of a mixture is equal to the sum of the masses of its components. So you can add them up. So H2, 6 kilograms, O2, 32, you just add them together. H2 plus O2 is 38 kilograms. So very straightforward. And then, so that's for the mass. And then the number of moles of a non-reacting mixture is equal to the sum of the number of moles in its components. Okay? So the number of moles of a non-reacting mixture is equal to the sum. So H2, 3 kilomoles, O2, 1 kilomole is 4 kilomoles. Okay? And then here it just tells you about the sum. The sum of the mass in mole fractions of a mixture is equal to 1. Of course, because when you have one system, if you have a glass of water, or let's not do water, something else, some other type of mixture, then when you're looking at what parts, if this is one mixture and if this is another mixture, you would want to look at this on 100% level, right? So it's all going to equal to 1 or 100%. Here, it just gives you the average of the molar mass. So, of course, if you can take it and break it down into a function, then you can also take averages, things like that. Of course, we have some constants, gas constant, the molar mass of a mixture, we looked at that already. And then you can do the relation between the mole and mass fractions of a mixture. And so here it's just it yields a fraction, of course, because that's just the relation between those. So then when we get into ideal and real gases and the PVT behavior, so Dalton's law of additive pressure for a mixture of two ideal gases, this is it. So if you have gas A and gas B, the gas mixture is going to be A plus B, right? So you're just going to add them, and then PA plus PB. So just combining the two, right? And then the predictions of the PVT behavior of a gas mixture is usually based on the two models. So the Dalton's law of additive pressure, the pressure of a gas mixture is equal to the sum of the pressures each gas would exert if it existed alone at the mixture temperature and volume. So what it does is it says, hey, you've got, let's take that H2O or H2O2 example. So if you have that, then what you would do is you would look at it on an individual level. And you would say, well, what kind of pressure, I know it has to be a gas mixture, but what kind of pressure would this specific individual gas exert if the conditions, if the environment were the exact same? Okay, and so say you get 5, so and then what would this other gas that we haven't mixed yet, what would this exert if it was at the same temperature, same volume, same environmental constraints? What would that do? And if that's 3, then you would just combine them together. So you look at them individually, and then you add it together. And then Amagat's law of additive volume for a mixture of 2 ideal gases. So you just have gas A, gas B, and then again you just see that that's combined there. And what that says is it says that the volume of the gas mixture is equal to the sum of the volumes each gas would occupy if it existed alone at the mixture temperature and pressure. So the same as Dalton's law, but looking at it from a volume law. Okay, so you would just look at it individually under the same circumstances and then just combine those and add them together. Here is the relation or the equation for Dalton's law and for Amagat's law, and then as well as the schematics for it. So PI is component pressure, VI volume, PI over PM is the pressure fraction, and then the same for volume fraction. And then for ideal gases, Dalton and Amagat's laws are identical and given identical results. So that's wonderful. They kind of proof each other. And so then here, exact for, I think that's supposed to be 4. Let's change that. Exact for ideal gases, and then it's approximate for real gases. So we are able to get it for ideal gases, but it gets kind of close, pretty close for real gases. And then the volume a component would occupy if it existed alone at the mixture T and P is called the component volume for ideal gases. It is equal to the partial volume. So you can think of the component when you're looking at the volume of a component would look like, and it's to trigger the thought of an individual, right? If it existed alone, if it was just one part. And that's because you're looking at mixtures overall, but you need to remember to take it on an individual level to get those data points. So ideal gas mixtures, here's some of the formulas that we've already looked at, but this is it in relation to PV, right? So this equation is only valid for ideal gas mixtures as it is derived by assuming ideal gas behavior for the gas mixtures in each of its components, of course, because we've got to look at the components first if we're going to get to the mixture. And so, of course, if we're using the formulas that are for ideal gases and we're combining them and putting them together, then it's only valid for ideal gas mixtures. So the quantity YI/PM is called the partial pressure, and it's identical to the component pressure for ideal gases. The quantity VI/VM is the partial volume, and it is also identical to the component, but the volume for ideal gases. So just a note here, for the ideal gas mixture, the mole fraction, the pressure fraction, and the volume fraction of a component are identical. Okay? The composition of an ideal gas mixture, such as the exhaust leaving a combustion chamber, is frequently determined by the volumetric analysis, or the ORSAT analysis. Here is the real gas mixtures when we start taking in account for additional information like ZM and that compressibility factor. So ZI is to determine either at TM or VM, Dalton's law, or TM or PM, Amagat's law. For each individual gas, using Dalton's law gives more accurate results here. And then here's just those same formula over here. Okay, and then one way of predicting the PVT behavior of a real gas mixture is to use the compressibility factor. And then moving on to K's rule. So Zm is determined by using these pseudocritical properties. And so here we have both of these. And then the result by K's rule is accurate within about 10% over a wide range of temperatures and pressures. So that's really nice because we've been using a lot of formulas here that says, oh, well, at low pressures it's accurate. Or at minimal temperature ranges it's accurate. But here you can get about within 10% of a wide range of temperatures and pressures. Another way of predicting the PVT behavior of a real gas mixture is to treat it as a pseudo-pure substance with critical properties. Extensive properties of a gas mixture, so you have UH and S here, and then changes in the properties of a gas mixture, and then you have those, just the delta. And those are in kilojoules and kilojoules Kelvin. Okay, so it just gives you these formulas. Extensive property of a mixture are determined by simply adding the properties of the components. We talked about that, so you just add them together. Intensive properties of a gas mixture, here we have UHSCC, and they're all on a mass basis. Properties per unit mass involve the mass fraction, MFI, and properties per unit mole involve the mole fractions, YI. The relations are exact for ideal gas mixtures, and approximate for real gas mixtures. So we talked about that. Okay, and then here it is. The intensive properties of a mixture are determined by the weighted average. So here, if you want to find the intensive properties, because it's on a mass and molar basis, we need to determine it by the weighted average. So the weighting average. So then when you look at the Gibbs-Dalton law, under the ideal gas approximation, the properties of the gas are not influenced by the presence of other gases. And each gas component in the mixture behaves as if it exists alone at the mixture temperature, Tm, and mixture volume, Vm. So what does that mean? That means that you could get a mixture already. The mixture can exist already. Say you're in a lab, right? So say you receive a mixture. You can't unmix the mixture. You can't unmix the exhaust leaving the car. You can't do that. But if you know the quantities within the mixture, if you know what is going into it and what is coming out, then you can look at the properties of each individual component of that mixture, and then calculate what is happening in that mixture. Right? Also, the HU, CV, and CP of an ideal gas depend on the temperature only and are independent of the pressure or the volume of an ideal gas mixture. So this is just saying that it's temperature dependent. We've learned that a lot of things are heavily temperature dependent. Partial pressures, not the mixture pressure, are used in the evaluation of the entropy changes of ideal gas mixtures. So again, we're looking at it on a component, not the mixture. It is difficult to predict the behavior of non-ideal gas mixtures because of the influence of dissimilar molecules of each other. So that's why we get approximate answers and we don't get exact, because it's very difficult. It's very difficult, in my opinion, working with non-ideal gases versus ideal gases, because ideal gases seem to be very straightforward. When you have an ideal gas or an ideal gas mixture, well, then you know that you can look at it just from ideal gas. If you have an ideal gas mixture, well, then you know that you can just look at it from its components of ideal gases, and it's just pretty straightforward. You have certain formulas that you use with those, that they're only applicable there. And it's like there's one or two paths to get there. But when you start looking at non-ideal gases and non-ideal gas mixtures, well, then you start approximating, you start having to make a lot more predictions and look at a lot more formulas to see what is applicable to that particular situation. TDS relation for a gas mixture. This equation suggests that the generalized property relations and charts for real gases that developed in 13 can be used for components of the real gas mixtures. So it's just saying that, hey, these generalized property relations and charts for real gases, we can use these for the components. But TR and PR for each component should be evaluated using TM and PM. Okay? If the VM and TM are specified instead of PM and TM, evaluate PM using Dalton's law of additive pressure. So this is telling you, hey, if VM and TM are specified instead of PM and TM, evaluate your pressure using Dalton's law of additive pressure. Right? Another way is to treat the mixture as a pseudo-pure substance having pseudo-critical properties. Right? We just said that. Determined in terms of the critical properties of the component gases by using K's rule. And remember, if you use K's rule over a wide range of temperature, over a wide range of pressure, you do get within about 10%. So that was a really quick one. It just, more importantly, wanted to talk about what a gas mixture is, how you can get it on mole and mass fractions, and how you can put those together to get a relation. The PVT behavior of gas mixtures, ideal and real gases, and then just the properties of a gas mixture, ideal and real gases, and then, of course, the formulas that you can use to accompany those.